So we've gone through the different sort of tools needed or that we could apply using the calculus of thermodynamics. And one of the useful things that we could do with these tools is we could use them to derive what we call equations of state. Equations that relate to the pressure, volume, and temperature of our systems. And we could derive these equations starting from our microscopic models. Okay? All right, and so to demonstrate this, what I want to do is I want to go through an example of how we could relate the microscopic entropy model we derived back in chapter 5.5. I want to relate that to an actual measurable pressure. Okay? And so what we're going to do is we're going to start from our ideal gas model for entropy. Okay? And so just as a reminder, for an ideal gas, we derived that the entropy was equal to this. Squared to the 3/2 plus 5/2. Okay? Alright, so this is our entropy model. And if we go to our fundamental internal energy equation, we have this. Where we know that based on the form of our fundamental internal energy equation, the partial derivative of internal energy with respect to entropy at constant volume is equal to temperature, and the partial derivative of internal energy with respect to volume at constant temperature is equal to negative pressure. Okay? Alright, now if we apply the triple product rule at this point, what we could show is that if we took those two partial derivatives, this one and this one, and divided them like this, based on the triple product rule, we would know that this ratio is equal to this. Okay? Right? So we're kind of applying the triple product rule backwards. Okay? To go from here to here. But essentially, we know what these partial derivatives are equal to. And they're equal to negative pressure over temperature. Okay? So these negatives cancel. And what we get is that pressure is equal to T ds dV at constant U. Okay? Alright, so we have that pressure is related to both temperature and entropy via this relationship. Okay? What we could do now is, since we have this model for entropy, we could actually just take the derivative of it with respect to volume and holding internal energy constant. Okay? So let's do that. So P is equal to T, and then d dV, and we're just going to throw in our equation. plus 5/2. Right? And so at first glance, this kind of seems like a nasty equation. But the useful thing is we're dealing with logs here, right? And so since we're dealing with logs, we could apply the properties of logs to help us out. So pressure is equal to temperature dV. So we have NkB. And what we could do is, we're taking the partial derivative of entropy with respect to volume. And so what we could do is we can manipulate our log so that we could just isolate the volume term. And then we move everything else out of the way, since they don't depend on volume. Okay? All right, and so when we take the derivative, the only thing we're taking the derivative of is that natural log of volume. And so what we end up with is NkB. Oh, forgot the T. NkB T over volume. Okay? Right, so a very simple result. And we could go even further, where if we say that our number of molecules here is basically equal to the number of moles we have times Avogadro's number. Right? Once again, Avogadro's number is just the number of molecules that are in 1 mole. Okay? So if we take moles times Avogadro's number, that would just tell us the number of molecules we have. Okay? So we're going to rewrite our equation like that. So we're going to have N NAV KBT over V. And if we have Avogadro's number times Boltzmann's constant, that's equal to the gas constant. And so what we get in the end is that P is equal to nRT over V, which you know as the ideal gas law. So something you've seen since high school. Okay? All right, so that's how the ideal gas law is derived. But what I want to remind you is that this ideal gas law is based on very specific and quite restrictive assumptions. Okay? And those assumptions where molecules don't interact with one another, and they could even overlap one another. Right? So essentially molecules don't see or sense one another. And these assumptions are really only valid when your system is at low pressure or a high temperature and volume. Okay? Right? So that's the only conditions in which the ideal gas law actually is relevant at all. And for most realistic systems that we deal with in life, they don't satisfy those ideal gas law assumptions. And so if we want actual useful estimates of anything, we're going to need more sophisticated equations of state, or PVT equations of state, that are able to describe, non-idealities in our gases. And also, we could use them to describe non-idealities in liquids and solids as well.